Okay, let's start. In the last lecture, we were talking about what is vector. Vector is the matrix with only one column. It's called the column vector, or just called a vector. Vector, for example, a vector with a 2 entry looks like this. So we can represent the vector with any real numbers looks like that. So we represent the vector looks like this. So we lead to this one is R2, right? R3, R4, something like this. So there was the two operation, vector addition and scaling vectors, right? So you can solve some vector operation, and we can represent the arbitrary vector in the 2D plane or the 3D space, something like this. So in the R2 case, it can be represented in a 2D space, x1 and x2, something like this, right? And we generalize the R2 vector into the R3 or Rn vector, something like this. So in case of R3, it can be represented in a 3D space, something like this, right? And there are several kinds of property of the vectors, right? So I showed the very simple proof, but you can prove the whole property by yourself, right? And there is the definition, the linear combination of the vectors with the scalar weight C1, C2 through the CP looks like this, right? Y is equals to C1 times V1 through V1 plus C2 times V2 plus blah 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 plus CP times VP, something like that. So this is the linear combination of the vector, right? So for example, if we have a two vector A1 and A2, and if we have a vector B, we can represent the vector B in terms of the A1 and A2. Then we can find the weight x1 and x2 that satisfy this linear combination. So in other words, this x1 and x will be the solution of this vector equation, right? So here was the example, right? So yeah, something like this, right? So yeah, there was one more definition called the span. Span V1, V2 through the VP is called the subset of Rn spanned by V1, V2 through the VP. Then what was the span? What was the span? The span was the collection of whole vector that can be represented in a form like this. So C1 times V1 through V1 plus C2 times V2 plus CP times VP. So this is the linear combination of the vectors with the weight C1 through the CP. So this is the definition of the span. So what was the geometric description of span? If the span V with the vector V, a non-zero vector in R3 space, then the span V is just a straight line, right? Through the V and 0, right? So this is the geometric description of the span V. Then what is the geometric description of the span U, V? Because now we have the two non-zero vector, so the span UV is the linear combination of the vector UV, and which can be represented like the C1 times V vector V plus C2 times vector V, something like this. So as bearing the parameter C1, C2, these values can be the plane on the 3D space, right? So this is the geometric description of the span, right? Then we will talk about the matrix equation AX equals B. So here was the definition: AX matrix A times vector X can be represented in a column vectors of A like this with each entry in the vector X. Then with this operation, this A times X can be represented like the linear combination of each column vector A1, A2, AN with the scalar value x1, x2 through the xn, right? Then what does that mean? What does it mean? What does it mean? What does it mean? It is related to the span, right? Right? So what does it mean? So 8 times x will be the span of the a1, a2 through the an vector, right? With the arbitrary scalar value x1, x2 through the xn. So okay, let's see here. So what does that mean? Okay, we will talk about that the goal of this section or this chapter is ax equals b, to solve the ax equals b. So we now know that ax is the span of what? Column vector in A, right? Then what is the span of this column vector? What was that? In third case, it was the plane, right? So it looks like this. It will be some kind of plane, and then let's say we the vector b here. Let's say this is a vector b, right? Like that. Okay, let's think about that. Okay, so in the matrix equation, in the left hand side, this left hand side will be the plane. It means that the point that satisfies this left hand side should be on the plane, right? What about right hand side? Right hand side is just the point or vector, but if this vector b is on this plane, there is a solution, right? Because it shows that there exists the vector x, right? That satisfies this equation. But if the vector b is not on this plane, there is no solution. It means that there is no parameter x that satisfies this equation, right? So this is the column representation, or the what to say. So this is the column representation of the ax equals b, right? Okay, so here was the example. Let me hit that, right? So ax equals b is called the matrix equation, right there. So here was the very, very important what's the theorem, right? Right. So ax equals b, the matrix equation, has the same solution set of the vector equation. Column vectors of A with the coefficient x1, x2 through the xn is equal to b. This was the vector equation. So they have the same solution, right? So what does that mean? Okay. To recap, we have some kinds of linear system, okay? Linear system. Let's say, what's that? Okay, a1 x1 through the an xn p1, right? Through the, let's say, a1, something like this. Yeah, like represent like this. Okay, so let's say x1 through the a2, something like this, something like this. Yep, a m1 x1 through the a m yeah, a1, yeah. What was that? What is that? Should the xn p m, and it should be p n, right? N, right. Anyway, so let's say this is the general formulation of the linear system. So we were talking about that we can represent this linear system as ax equals b, right? In this case, each element in the matrix A is 1 or 2 1 am1 through the amn a 1 and something like this. So the size of the matrix A was the m by n, something like this. So in this case, the size of vector x should be what? N by 1, right? It's like x1, x2 through the xn. And the size of vector v should be what? N by 1, something like this. So we can represent any linear system in a ax equals b form, right? So how can we solve this? There was the method to find the solution in a picture or the space. Let's say, okay, let's say this is the equation 1, this is equation 2, equation 3. Then first of all, we can represent this each equation as a plane in case of the three variable case, right? Something like this. So it means that this row vector determine this each equation, this each plane, right? So in this case, the finding a solution is to find the intersection of the each plane, right? Then what about this? If we think about this column vector of the matrix A, we can solve the solution using this column vector. Let's say there is A1, A2, then A3, something like this, and there is the vector B, something like that. Let's say that, something like that. Yeah, in this case, yeah, let's go ahead. So let's say this is a vector B, then we can say that the finding a solution of this Ax equals b is find the coefficient or magnitude of the each vector that make this vector by combining this one, and this one. So this is the column interpretation of the Ax equals b. So there is two kinds of interpretation of the solution in Ax equals b. So this is the general idea of this theorem. So it means that Ax equals b has the same solution set with the vector equation, this one. It means that this is a column representation like this of the Ax equals b. So this was the important theorem, right? So let's continue, right? So yeah, we also were talking about the computation of the Ax, right? So to compute the A times vector x should be this one is this row vector times this column vector, and this one is this row vector times this one. This one was this row vector times this one. So this is the rule of the a matrix and vector multiplication, right? Okay, let's move on to today's lecture. Today we will talk about the solution set of the linear system. Okay, so first of all, let's think about the homogeneous linear system. Here is the definition. The homogeneous system. A system of linear equation is said to be the homogeneous system if it can be written in the form Ax equals b. Ax equals b. Here, A is the n by n matrix. X is a vector in the Rn. The zero. This one is the zero vector in Rm, right? Until last lecture, we will talk about the Ax equals b with the arbitrary vector b. But here now on, we are talking about the homogeneous system like this. So let's think about the correlation between Ax equals b and Ax equals 0. So anyway, so in the homogeneous system, there is at least one solution. It means the trivial solution. Trivial solution is x equal 0. What does that mean? Okay. Let's say the matrix A is equal to A1 through the AN, something like that. Then what is the vector equation of this one? A1 x1 plus A2 x2 plus through the AN xn equal to 1. What makes this equation satisfying? When x1, x2 through the xn equals 0, it satisfies this equation, right? So it means that the vector 0 vector means there are 0 at each entry. So this is 0 vector here. So for every homogeneous system, they have the trivial solution. And if there is the non-zero vector x that satisfies Ax equal b, not x equal 0, but if there are non-zero vector x that satisfies Ax equal b, it is called the non-trivial solution. Okay, so here is the definition. So the Ax equals b has a non-trivial solution if and only if the equation has at least one free variable. at least one free variable. What does that mean? If there is at least one free variable, there exists infinitely many solution, right? So in this case, so not only x equals 0 is solution, but also there exists another non-zero vectors that satisfy x equal b. Okay. So here's example. Okay, determine if the following homogeneous system, right? This one has a non-trivial solution. And then describe if there is the non-trivial solution, describe the solution set. Okay. Okay, first of all, why this system is the non-trivial homogeneous system? Because it can be represented in a ax equal b, right? Because this one, right hand side is the vector b, right? Okay, so first of all, to solve this linear system, what should we do? What should we do? In the last lecture and 2 weeks ago, we were talking about the row reduction algorithm, right? So to solve this linear system, first of all, we have to reduce this linear system in a matrix form, okay? So let's say matrix A is the matrix of the coefficient, and row reduce the augmented matrix of this system to echelon form. Do you remember what was the echelon form, right? So here is the solution. So okay, so the augmented matrix form of this linear system, it looks like this. This is the coefficient matrix, right? A, and this is the right hand side vector B, right? So to convert this original matrix into the echelon form, what should we do? First of all, we have to remove this part, right? How can we do that? How can we do that? Let's say this is the row 1, row 2, row 3. How can we do that? To make this part as a 0, we can just add row 1 and row 2, right? So it make new row 2 like this. And how can we do that? We can replace our original R3 with the R3 what? Negative 2 times R1. Then it remove this one and make new R3, right? This is the just one step, and after finishing this one, we can go ahead on this sub matrix like this. So finally, we can get the echelon form. Looks like this, right? You can do that now. By the way, there will be the homework next week. So in the homework, you can solve the echelon form and the reduced echelon form yourself. So yeah. So in this case, x3 is a free variable, right? So ax equals b has a non-trivial solution. Well, what does that mean? Yeah, let's see the final row reduction algorithm. Okay, so yeah, from the echelon form of the matrix, we can convert this echelon form into the row reduced echelon form called REF, right? Like this. Do you remember how can we do that, right? Remove this part. No, not this part. Remove this part using this one, right? And then make those values as a 1. Looks like this. Then what is the parametric description of the solution? Because there is x1, x2, x3. So the first row, in the first row, x1 minus 4 over 3 times x3 is equal to 0, x2 is equal to 0, 0 is equal to 0, right? So in this case, x1 and x2 are basic variable, and then x3 are pre-variable. Then x1 can be represented in terms of the x3 looks like this and looks like this. So then how can you represent the x1 and x2 and x3? Here we can just replace this one and this one here, right? Then like this, because x3 is a pre-variable, then x3 can be any values in real numbers, right? So we can represent this one, looks like this, x3 times the vector, this one. Okay, let's say this is the vector b, and this is the pre-variable, right? Okay. Actually, it can be the any kind of the scalar value, right? Scalar in what? In this case, just real value, right? Scalar value, right? So what does that mean? The solution that we want to solve, that we want to get, is the linear scaling of this vector v, right? What does that mean? So vector v was like this, then this is a vector v, then the solution x will be the scalar multiplication of the vector v, so it will be looks like this. It will be the straight line in the 3D space. Then what is that? Actually, this is the span of the vector v. Why? What was that? Span of the vector v was the linear combination of the vector v with the vector v, right? So in this case, c is equal to x3, right? So anyway, so solution set of this problem is a line through the x 0, looks like this. So in this case, there are several or infinitely many non-trivial solutions. Here, every point on the line, and it includes the trivial solution. What was that? Trivial solution was x equal to 0, obtained by choosing x3 is equal to 0. So it means that when x3 is equal to 0, this value will be the 0. So this solution will be the 0, right? So this is the solution of the homogeneous linear system. Okay. Here is one more example. Okay, let's say here is the linear system, very simple linear system with a single equation. Okay. Anyway, this is still homogeneous system because this can be represented Ax equals B, right? In this case, A is just 10, 3, right? Anyway, this is a homogeneous system. Then describe the whole solution of the homogeneous system. Okay, how can we do that? In this case, this is x1, x2, x3, right? In this case, this is the x1 is the basic variable, the single basic variable. However, x2 and x3 is the pre-variable, right? So what is that? x1 can be represented like this in terms of x2, x3, right? x2 and x3 was pre-variable, right? So what is the parametric description? Parametric description of the solution? Do you remember, right? x1 0.3 times x2 plus 0.2 times x3, and x2 is free, right? x3 is free, right? So this is a parametric description of the solution, right? So it can be represented in a vector form, looks like this, right? The solution vector x is equal to x1, x2, x3, and x1 is like this, like this, like this. Then, what is that? Then, how can we decompose this one? Okay. Let's write like this again. x2, 0, plus we can decompose this one into this one, right? With some basic property of the vector, right? Then how can you do that? We can represent this one with x2 times this vector, x3 times this vector, right? Right. So now let's say vector u is like this, vector v like this. It means that, okay, let's say this is the vector u, this is the vector v, right? And this is just the scalar weight, right? So what does that mean? X is some kind of the scalar value with the vector u plus some kind of scalar value, let's say t and c, yeah, and v, like this. What does it mean? So because we have the vector u and v, then the solution x will be the represent in terms of the vector u and vector v. In other words, the vector solution vector x is the linear combination of the vector u and vector v. Okay, so vector u and vector v. So linear combination means, what is that? This is the span of vector u and v. Okay, span of the x u comma v. What does it mean? As varying the t and c, we can determine the so many solution here. They will establish the plane on the 3D space according to the vector u and v, like this, right? So the solution of this homogeneous linear system will be the plane, right? Okay, so here is one more definition. From these two example, there was a two example, right? So from these two example, we derive the solution vector x in a form like this. The linear combination of the vector u and vector v with the weight values s and t in the real space. Okay, in this case, in this form, we call this form or this equation as a parametric vector equation. Okay, so the solution x is equal to su plus tv is called the parametric vector equation, right? So whenever solution set is described explicitly with a vector, we say that solution is in the parametric vector form. So yeah, this was the parametric vector form of this problem, and yeah, this is the parametric vector form of this problem. Okay, so here is the definition. Okay, so to summarize, to write the solution set of the consistent system, consistent mean? Do you know? Right? The existence of the solution. Okay? If you can't follow this line, please go back to our previous lecture in our YouTube. Anyway, so to write the solution set of the consistent system in a parametric vector form, there are 4 steps. First one is row reduce the augmented matrix to a RDF form, right? And then express each basic variable in terms of pre-variable. Okay. So it was the parametric description of the solution, right? And then write the typical solution X as a vector whose entries depend on pre-variable, like this, okay? And then decompose X into the linear combination of the vector using pre-variable as a parameter, like this. Decompose this one as a vector with the parametric constant coefficient x2 and x3. So this is how to write the solution set in the parametric vector form. Okay, let's move on. We were talking about what is the homogeneous system and how to solve the homogeneous system. Okay, now let's go back to the non-homogeneous case. Then what is the non-homogeneous system? Ax equal b. Okay, because the homogeneous system was Ax equal 0. So what is the solution of the non-homogeneous system? Here is some description. The general solution of the non-homogeneous linear system can be written in parametric vector form as the one vector plus an arbitrary linear combination of the vector that satisfy the corresponding non-homogeneous system. What does it mean? Okay, let's say we have Ax equals b, the non-homogeneous system that we want to solve. Then we have a corresponding homogeneous system like this, right? Because the matrix A is exactly same as this one. Okay, let's say the solution of this non-homogeneous system as a x non, then and the solution of the homogeneous system as a x yeah, looks like this. Then what does it mean? The solution non-homogeneous system is the just arbitrary vector, let's say u, plus arbitrary linear combination, let's say c times x homogeneous. So what does it mean? If we have the solution of the corresponding homogeneous system here, then we can represent the solution of the non-homogeneous system as a particular vector u plus the linear combination of the homogeneous system. Okay, so let's see the example. Describe the whole solution of the Ax equals b non-homogeneous system where A is like this, B is like this. Especially this coefficient matrix A is exactly same to this system, right? So this system was the Ax equals b, right? But in this case, there is the additional vector b. Okay, then how can you do? First of all, we should row reduced this augmented matrix like this. This is a coefficient matrix, and this is the right hand side of the system. Then we can derive the row reduced form from the row reduced echelon form from the original matrix. Yeah, you can do that. Please do it yourself. Derive this REF form of the original matrix from this original matrix. Okay. Anyway, if we find the REF form of the matrix, we can represent the solution in a parametric solution form. So let's say there is x1, x2, and x3, right? Because the x1 and x2, the columns of the x1 and x2 has the pivot position. So x1 and x2 are basic variables, right? And x3 is the free variable. It means that we can represent the x1 and x2 in terms of the x3, free variable x3, like this, like this, like this. Then x3 is equal to -1 plus 4 over 3 x3, and x2 is equal to 2, and x3 is free, right? Then we can represent the general solution of the ax equals b in the vector form, like this. Vector x is equal to x1 and x2 and x3. What was x1? x1 here, x2 here, right? So the first entry is the -1 plus the 4 over 3 x3 and 2 and x3. Then how can I decompose this? This is the only constant, and this is the entries or terms with the x3, right? Then we can decompose the original or general solution x as some arbitrary vector plus linear combination of the some vector. Okay. Let's say this vector as a vector p, this vector as a vector v. Then this solution can be represented x plus p. X is equal to p plus x3v. If we write the t as a general parameter instead of the x3, we can generally represent the solution x is equal to p plus tv when t is in the real numbers. Then this equation describes the solution of the ax equals b in the parametric vector form. Okay. So what does it mean? We want to find the solution of the ax equals b, but we can represent the solution x in the parametric vector form. Looks like this, right? But if you remember the previous example, the solution set of the ax equals b, ax equals 0, has the parametric vector equation x is equal to tv, right there, with the same vector v, right? This one and this one, right? Those two vectors are exactly the same, right? Then what is the difference between this one and this one? What is the difference between the solution of the ax equals b and solution of ax equals 0? Here, right? The only difference are here. What does that mean? What does it mean? The solution of the ax equals b are obtained by adding the vector p to the solution of ax equals 0. Okay. So the solution of the ax equals b is the can be represented by adding the solutions of Ax equals 0 with the vector P. Okay? So this is a very important property. Here, vector P itself is just the one particular solution of the Ax equals B when T is equals 0, right? So when T is equal 0, X is just vector P. So the vector P is the particular solution, one particular solution of Ax equal B. Okay. So let's see this solution in the geometrical manner. Okay. Okay. First of all, to describe the solution of Ax equals B geometrically, we can think about vector addition as a translation. What does that mean? Okay. Let's say if you remember the vector addition, we have a vector P and vector V, and the vector V plus vector P is looks like this, right? Vector P, vector V, or vector V or vector P, right? In this case, we can say that vector V is translated by P to V plus P. What does it mean? Vector V is translated by P, this vector P, to this one, right? In this case, adding P to the V translate V to the VP. This is very intuitive, right? Right? If we have any vector like this, let's say this is V, and we have a vector P like this, then we can just move this vector V to the same vector P like the V plus P, right? Right? Then let's say each point on the line L, let's think about the arbitrary line L like this, right? Like this, is translated by the vector P. Let's say this is the vector P, okay? That's a vector P. Then the result another line parallel to the original line L. So the original line moved to the L plus P parallelly. Okay. So to summarize, the Ax equals P plus TV. This was the general solution of the Ax equals B, right? Right? And V was the solution of the Ax equals 0, right? Then X is equal to P plus TV is the equation of the line through the P parallel to V. What does it mean? Let's see the figure here. Okay. Here is summarized. So the solution set of Ax equals B. The solution set of Ax equals B here. Okay. Let's assume that the solution set of the Ax equals B is just a line like this. Then through the P, here's P, parallel to the solution set of Ax equals B. Okay, if there is a solution set of the Ax equals B here, right, then we know the solution set of Ax equals B can be represented some linear combination of the vector v, right? So as a line, right? Then what was the solution set of this one? What was that? Some arbitrarily vector p plus the linear combination of the solution of ax equals 0, so plus cv, right? So this is the solution of the ax equals b, so it will be the line like this, okay? Because this is the c vector v, right? Then when we add the arbitrary vector p to the cv, it just shift. It can just to shift the original line L to the this line, right? So this is the solution of the ax equals b, okay? So this relationship between the solution set of ax equals b and ax equals 0 generalize any consistent equation ax equals b, although the solution set will be larger than the line with the several pre-variable. What does that mean? In this case, we just assume that the solution set of ax equals b is just a line, right? Like, let's go back, like this one. Then what about this? This is a solution set of this linear equation and this homogeneous linear equation. But in this case, there are two pre-variable, right? x2 and x3. So the solution set of this linear system was the plane, right? Then this property can be generalized to the more pre-variable case. Let's say the plane case. So let's think about a higher dimensional interpretation of this one here. Okay, so let's say the solution set of the ax equals b, the homogeneous system here. Then we want to solve the ax equals b, the non-homogeneous system. Then in this case, the solution of this non-homogeneous system is the vector p plus linear combination of the homogeneous system. So in this case, the solution of the ax equals b is just a shifted plane from this plane, right? So the solution of the ax equals b is just a parallel in the 3D space to the ax equals solution of the ax equals b. Okay, so it looks complicating, but you can remember the properties here, and then we can generalize this one to the 3D plane case, right? So here is the summarization. Here is a theorem. Okay, suppose equation ax equals b is consistent or has a solution, right? For some given b, and let p be a solution. Then solution set of ax equals b here, ax equals b is the set of the whole vectors of the form w is equal to p plus vh. So p is the particular solution of the ax equals b, and vh is the any solution of the homogeneous equation ax equals b. So this equation makes this translation in the 3D space. Okay, so this theorem says that if ax equals b has the solution, then solution set is obtained translating solution set of the ax equals b. Okay, using any particular solution. Okay, to summarize, to find the solution of Ax equals B, we can find the solution of Ax equals 0 in a homogeneous representation, and find any particular solution P. Then we can represent the solution of this one as a P plus VH, like this. Okay. So this is the relationship of the solutions of the homogeneous and non-homogeneous systems. Okay. Okay. Here is some question. Suppose the equation Ax equals B is consistent and has a solution, right? Then how can we use the solution of Ax equals 0, homogeneous solution, to determine the solution of Ax equals B is the unique or not? Okay? Please remember this one. Let's say the solution of the non-homogeneous case is a particular vector P plus linear combination of the some vector that satisfy the homogeneous equation. Let's say VH, right? So yeah, how can we determine if the solution of Ax equal B is unique or not? Okay, this particular vector is unique, right? If the solutions of the Ax equal 0 are infinitely many solutions, then the solution of this one is also infinitely many solutions, right? But if there is the no trivial solution, non-trivial solution, there only exists a trivial solution. In this case, the solution of this one is just P, right? So if the homogeneous system Ax equals B only has a trivial solution as x is equal to 0, then in this case it will be just P, right? So in this case